All right. Um, as you know, this is the last day of in-person instruction for the semester. So it's very important from here to the end of the semester that you check your email regularly. Hopefully, most of you do that, but some of you might not be in the habit of doing that because that's the way I can announce things to you. That's the way I can communicate with the whole class is by sending out emails. So any announcements that we have, descriptions of how you're going to take exam 4 and how you're going to take the final exam remotely. Those things are going to come in due time by email. So make sure that you're checking your email frequently. And then, of course, Learning Suite as well, because all of the lectures from here on out are just going to be recorded and links posted on Learning Suite. Office hours are going to be virtual, so there will be Zoom links posted on Learning Suite. So Learning Suite and email are going to be very important for us. I know that it kind of seems like the last day of the semester for us right now, but it's definitely not. We still have many important topics, and we still have about half the points of the class remaining. So it's important to stay very engaged in the class, even though we won't be physically in the same room. So today we are going to finish our discussion of IR spectroscopy, and then we will begin our discussion of NMR spectroscopy, primarily focusing on an introduction to the topic, studying a little bit the physics behind the technique so that we can understand what's happening when we're performing NMR spectroscopy. Where we left off with IR was this very nice table right here that divided the IR spectrum into 4 sections where the positions of the stretches of these types of bonds is intuitive based on our understanding of Hooke's law, where the bonds to lighter atoms will vibrate at higher frequencies, and stronger bonds also will show up at higher frequencies as well. Your book also has a table of important IR absorptions. Please don't memorize this table. There are only 2 numbers that are important to memorize, and that's 3,000 and 1,700. Okay, you don't need to memorize all of these numbers. If I made a table and called it important IR absorptions, there would only be 3 entries. So one of them would have part A, B, and C, but there's essentially only going to be 3 entries in our table of important IR absorptions. Okay, because many of the ones that are less important, in my opinion, the information that you would get from them is more easily obtained from an NMR spectrum. So we're going to focus on the information that is most easily obtained from the IR spectrum, and we're going to ignore the other things that you can learn easier from an NMR spectrum. But the first thing we'll look at is right here at the top of the table, and that is the OH or the NH stretch. And we'll look at a spectrum and we'll see that those stretches are very strong and very broad. The table here tells you that the OH is stronger than the NH. Frequently that's the case, but not always, as we'll show you. If we go back to this spectrum of an alcohol, 1-propanol, we see a very strong, very broad OH peak. So I told you yesterday that the peaks in an IR spectrum are broader than the peaks in a mass spectrum. They're broader than the peaks in an NMR spectrum, which we'll see later today. And we gave one reason for that yesterday. We said that there are many different rotational energy levels superimposed on the vibrational energy levels, meaning that a molecule can be in gauche or an anti or an eclipsed conformation about its various carbon-carbon bonds. And so that leads to fat peaks. There's another reason why the OH and the NH peaks are broad, and that is intermolecular hydrogen bonding. When you have a sample of an alcohol or an amine, those molecules are going to be held together by hydrogen bonds. So you're going to have aggregates of those molecules, and you'll have different aggregates that contain different numbers of molecules. And so based on the extent of the hydrogen bonding, you're going to have slight differences in the IR absorption frequencies for the OH stretch. If you have a hydrogen bond, that's going to impact the amount of energy it takes to cause that bond to stretch. So whenever you have bonds that are capable of hydrogen bonding, you're going to have a broad peak because of the impact of hydrogen bonding, the formation of these different aggregates due to the hydrogen bonds. Yes?
Will that only be true for the atom-second hydrogen bond, or will that influence the current peaks as well?
It's only going to influence the bonds where you have an atom involved in a hydrogen bond. So that would be the OH bond stretch or the NH bond stretch. And so those are the peaks that are going to be fatter due to the impact of hydrogen bonding. Okay, so the range, if we go back to our table, we see the range here overlaps. Sometimes you could say that the OH peak would be stronger than the NH, and that's how you could tell the difference. But there's another way to tell the difference. How would you tell the difference? How would you look at a spectrum that had a fat peak above 3,000 and know if it's an OH or an NH? Yes, Parker. Okay, so it is related to mass spec. The answer is not in the IR. You're not going to figure it out in the IR. You're going to figure it out by looking at the mass spec. And if you have an even mass for the small types of molecules we're looking at in this class, you can be pretty confident there will be no nitrogens. If you have an odd mass, you know that there will be a nitrogen. So that's the way you would use the mass spec to tell. There is, in some cases, when you have an NH, you do end up with two peaks, and we'll talk about that in a moment, but that's not always a diagnostic feature. Okay, so the second point that we'll look at, the second types of peaks we'll look at, are the CH stretches. And we had an iClicker question about this. The absorption frequency is going to be directly proportional to the bond strength. So our sp3 carbon hydrogen bonds are going to vibrate at a lower frequency than our sp2 carbon hydrogen bonds, which will vibrate at a lower frequency than our sp carbon hydrogen bonds. If you look at the table, you see that the sp3 carbon hydrogen bonds show up below 3,000, and the sp2 and spCH bonds show up above 3,000. So the number 3,000 is now important for two reasons. Above 3,000, if we have a fat peak, we know we have an OH or an NH, and it's the dividing line between sp3 carbon hydrogen bonds and sp2 or sp carbon hydrogen bonds. And we can see this by looking at some spectra. Here's hexane. We only have sp3 carbon hydrogen bonds. We take a ruler. If you have a clear plastic ruler, it's very helpful for looking at spectra. You could put that on this page and you would see only peaks to the right of the line going up from 3,000. So we only have sp3 carbon hydrogen bonds in this molecule. We look at 1-hexene. We still have plenty of sp3 carbon hydrogen bonds in this molecule, but now we have a sharp peak just above 3,000. In this case, that tells us we have sp2 carbon hydrogen bonds. And then we look at an alkyne, 1-hexyne. The peak's a little bit further to the left. In this case, it's really strong. It's not always this strong. Sometimes it's short, like the alkene. Sometimes the alkene and the alkyne CH stretches are close enough to each other that you might have trouble deciding which is which, but in the NMR it's unambiguous. So you don't have to decide from the IR if it's an sp carbon hydrogen bond or an sp2 carbon hydrogen bond. The NMR will tell you unambiguously which one it is. So what I like to do is just use 3,000 as that dividing line. Any peaks I see to the right are due to sp3 carbon hydrogen bonds, and most of our molecules will have those. And then if we see sharp peaks above 3,000, that tells us we have sp2 and or sp carbon-hydrogen bonds. If we see a fat peak above 3,000, that tells us we have an OH or an NH, and we can usually tell which one it is by looking at the mass spectrum. Okay? Questions? Yes. Ketone does not appear above 3,000 because it is a bond between large atoms, heavy atoms. Those heavy atoms show up usually 2,000 and below. But that's a good question because the third diagnostic feature of the IR spectrum is the presence of a carbon-oxygen double bond, or a carbonyl group. So the stretching of the carbon-oxygen double bond is very strong. It's usually the strongest peak, the highest or the lowest percent transmission, and it shows up between 1800 and 1650 inverse centimeters, or wave numbers, usually pretty close to 1700. So 1700 is the second number that you want to memorize in terms of IR spectroscopy. And there aren't other peaks that show up in that area. Carbon-carbon double bonds are kind of close, but they're usually much smaller. We're usually not looking for carbon-carbon double bonds in an IR spectrum. So here we have a ketone, 2-butanone, and we see this strong peak at 1700. That immediately tells us we have a carbon-oxygen double bond, or a carbonyl group in our molecule. Okay? And then if we go down here to 3000, we see we only have sp3 carbon-hydrogen bonds. We don't have sp2 or sp. We also don't see any OH or NHs in this molecule. Any questions? Yes? Yeah, anything that's this small you would ignore. There's noise. The baseline is wavy in this case. And so, yeah, the peaks usually have to be pretty good sized before you would pay attention to them. So sometimes with IR spectroscopy, you can use the absence of peaks to rule out certain functional groups. So we go over here and we look at the IR spectrum of diethyl ether. So if we knew that we had an oxygen, if the molecular formula only made sense with an oxygen, we see there's no peak at 1700, so there's no carbon-oxygen double bond. We see no OH, so what oxygen-based functional group has no carbon-oxygen double bond and no OH? There's only one, it's the ether. So you would know by ruling out certain functional groups due to the absence of peaks that you had an ether in this case. So sometimes the absence of peaks will tell you things about NMR spectroscopy as well. So symmetry will affect IR spectroscopy. So in order for a peak to appear in an IR spectrum, there must be a change in dipole during the vibration of the bond in order for infrared radiation to be absorbed. Okay? The reasoning behind this lies in some physical chemistry theory that it's been too long since I learned it, so I can't really explain it. But there are consequences of this principle in IR spectroscopy. So there must be a change in dipole as that bond is vibrating, stretching, or bending in order for IR radiation to be absorbed and a peak to be seen. So where this has a consequence is if we have an internal alkyne. And if these R groups are the same or very similar to each other. In molecules like this, as we stretch that carbon-carbon triple bond, there's no change in dipole because of the symmetry in the molecule. Okay? So what this principle means is that internal alkynes do not show up in the IR if they're symmetrical. If they're close to symmetrical, so let's say one R group is a propyl group and the other R group is a butyl group, that's close enough that the peak is going to be so small, it's just going to be down in the baseline. So many of our internal alkynes will not show a carbon-carbon triple bond stretch. Now, you could see the other peaks from other bonds stretching, but you wouldn't see the carbon-carbon triple bond stretch. So if we go back, here's our 1-hexyne. This is a terminal alkene. Hydrogen is very different from this butyl chain. So here we do see the carbon-carbon triple bond stretch. It's not a huge peak, but we do see it at about 2200. Of course, we see the sp carbon-hydrogen stretch. But if it were an internal alkyne, this peak could be small or non-existent. So that's what we mean by this principle right here. Any questions? Okay, so let's look at a few more examples of some nitrogen-containing compounds in the IR. So here we have octylamine, and this molecule is a primary amine, meaning that it has one alkyl group attached to the nitrogen, so it has an NH2. So here are the NH peaks, and I told you that in many cases they are smaller than OH. This is one where we see that. It's not always the case. We also see two peaks here. When we have two NH bonds, we see two stretches. It's not that the two bonds have different stretching frequencies, because those bonds are equivalent to each other because of rotation. What it means is that those stretches are coupled. And you can have the two bonds stretching in phase with each other, so they could be stretching like this. Or you could have them stretching out of phase, which would be something like this. Okay, so that's why you would see the two peaks. You have the in-phase coupled stretch, the out-of-phase coupled stretch. And then, of course, we see, we have our dividing line at 3000. We only see peaks here. We don't see peaks in this region. So we only have our sp3 carbon-hydrogen bonds. If we have an amide, we have a carbonyl group and an NH2 in this case. This is a carbonyl right here. It got cut off for some reason on this particular slide. And I guess I'm not even in the slideshow here, but well, that was the wrong button. I was supposed to press. Let's try that. Okay, looks a little bit better. Still cut off, but that's supposed to be a carbonyl there. So we see a carbon-oxygen double bond stretch at 1700, and then we see our NH. Remember I told you sometimes NHs are big, sometimes they're small. In this particular case, we had a pretty strong peak from the NH2 of our amide. And then we see the CH stretches here that show up relatively small in this particular case. Question, Parker? I'm not entirely sure, to be honest, what controls the strength of the peaks in this case, but it certainly can vary, as you saw from the previous one to this one. And then we have nitrogen functional groups with no hydrogens, no nitrogen-hydrogen bonds, the nitrile, the carbon-nitrogen triple bond. So this one does have a dipole, and that dipole will change as you stretch that carbon-nitrogen triple bond. So when you have a nitrile, you always will see a peak. So this is one. If we were to have a fourth one, we'd probably put the nitrile down. But because nitriles are less common than other functional groups, it's not as important as the ones that we have listed here. But if you knew you had a nitrogen in your molecule, and you knew that you had 2 degrees of unsaturation, then the nitrile is a possibility, and you could go looking for a peak at about 2200. Okay. Notice there's no NH, and we only have sp3 carbon-hydrogen bonds. Any questions? Okay, so let's look at a couple of sample problems. So here we have one where they're showing you a couple of spectra and asking you what functional groups are present, what types of bonds are present. That's the information we're trying to get from an IR spectrum. And so we just want to look in two places. We want to look at 1700 and 3000. So we look at compound A. We immediately see it has a carbonyl group, a carbon-oxygen double bond. We draw our line at 3000. We know that it only has sp3 carbon-hydrogen bonds. And we know there's no NH or OH. These are just really small. Okay. Then we look at this molecule. No carbonyl. We do have a strong peak here. Usually you don't see peaks this strong at 2200. In the practical world, that's where carbon dioxide would show up. So if you applied your sample, when you take an IR spectrum, you put a solution on a salt plate and you let the solvent evaporate. Sometimes you blow on it to make the solvent evaporate faster. And if you blow a lot of CO2 on it, then you'll see a peak from the CO2. And so that's what I would think as I looked at this, is that the person was blowing on their sample. But it could also be due to an alkyne or a nitrile. But then these peaks above 3000 are too small for you to think that there's either going to be an OH or an NH. Okay? Any questions about these? Okay, and then the last one we're going to look at is helping us figure out how to use mass spec and IR data together to come up with reasonable molecular formulas for a molecule. So the first thing we want to do, well, let me back up and say that there's more than one way to approach these kinds of problems. But there's a logical approach, an approach that's logical in my mind at least, and that is to start with the mass spectrum. To look at the mass spectrum, locate the molecular ion. They've helpfully given it to us here. And once we know what the molecular ion is, we want to divide that number by 12 to figure out the maximum number of carbons that could be present in the molecule. So when we divide this by 12, what do we get? 7, okay, good. And what's our remainder? 4, okay. So the most carbons we could have would be 7, and we'd have 4 hydrogens. But that doesn't make sense. That is, let's see, 16, that's 6 degrees of unsaturation. I don't know how you could have 6 degrees of unsaturation with 7 carbons. That wouldn't work very well, okay? So we need to take away a carbon, and we need to add either hydrogens or an oxygen. Could we add hydrogens to this formula? If we subtracted a carbon and added 12 hydrogens, would that be a reasonable formula? No, why not? It would be oversaturated. You have too many hydrogens. It would be an impossible formula, okay? So let's see what happens when we add an oxygen. If we're going to add an oxygen, we have to subtract CH4, okay, 16 to be able to match the mass of the oxygen that we're adding. That gives us C6Ho. Okay, that makes even less sense. So we know that we're going to have to take away another carbon and add some hydrogens in. Okay, so we'll add 12 hydrogens and subtract a carbon. So that gives us C5H12O. Is this a reasonable formula? How many degrees of unsaturation? 0, okay? So this formula would work. Is it consistent with the IR spectrum? So once we generate a reasonable molecular formula, we can now look at the IR spectrum and see if it fits. You're shaking your head no. Why? Okay, no OH, but couldn't we have a functional group, oxygen functional group without an OH? Okay, so is there something in the IR that tells us we have a degree of unsaturation? There definitely is. We have a very strong peak at 1700, so we know we have at least 1 degree of unsaturation. So we know that this formula doesn't work. So we can forget about that formula, and we have to do the same thing. Not the same thing as this. We have to add another oxygen. We have an even mass, and so we're not going to add nitrogens. You'd have to add 2, which is not impossible, but I told you it's pretty unlikely to have 2 nitrogens in the molecules of the size that we're studying. So we add an oxygen, we subtract CH4. So that gets us C4H8O2. How many degrees of unsaturation? Okay, 1, right? 10 would be fully saturated, 10 hydrogens. So 1 degree of unsaturation. Now we have a formula that fits our IR spectrum. Okay, so this could work. We should keep going to see if there are other possibilities. So let's add another oxygen, subtract another CH4. That gets us C3H4O3. How many degrees of unsaturation? 2. Okay. So it's not impossible, but it's going to be pretty hard to have 2 degrees of unsaturation and 3 oxygens when you only have 3 carbons. In fact, I can only think of 1 molecule that would fit that. Right? We could draw a structure like this that would fit that, and that would fit with this IR. We could very easily tell by looking at the NMR if this is correct or not. But there's going to be multiple structures that we can draw that are going to fit C4H8O2. But we do know, as was mentioned, there's no OH, right? So these would have to be structures that didn't have an OH. They would have either an ester functional group or a ketone and an ether separate from each other. So what we would do at this point is we would set aside the IR and the mass spectrum, and we would look at the NMR, and we would distinguish between the possible structures using the NMR spectroscopy. Okay, so IR is useful for ruling out certain molecular formulas and telling us which functional groups are present and which functional groups are not present. Questions? Yes, Noah. This one here? Yes. So the 1 degree of unsaturation here would have to come from a carbon-oxygen double bond because of that peak right there. There would be no other unsaturation. Down here, it could be 1 carbonyl and 1 ring. I guess we could have 2 carbonyls. I didn't even think about that one. So I guess we could have this is a really weird looking one though. That's not a very reasonable molecule. So here we have 2 degrees of unsaturation. At least 1 is coming from a carbonyl. Okay, other questions? Yes. One could be an ether. We know that only 1 can be a carbonyl because there's only 1 degree of unsaturation. If it's this formula. Oh, yeah. Yes. Okay. So IR and spectrum, you don't tell us really anything about whether it comes from the degree of unsaturation comes from a ring, besides the fact that we can see the C. Yes, if you have a carbonyl, you can tell that you have a degree of unsaturation from a double bond. If you don't, then you can't distinguish if it's a carbon-carbon double bond or a ring. Right, you need to look at the NMR. The NMR gives you so much more information. So you would stop looking at the IR at this point and move on to NMR, which is what we're going to do now. So NMR spectroscopy, as I mentioned, is our most useful technique that we have. And the N stands for nuclear, meaning that the energy levels that we're dealing with are nuclear spin states. Okay? So, and the type of radiation we're using is radio frequency radiation, or radio waves. This is the lowest frequency, lowest energy of radiation that we have in the electromagnetic spectrum. And what we're relying on in NMR spectroscopy is the fact that a nucleus has a property called spin. Okay? This is a property that comes from quantum mechanics, something that you'll learn more when you take physical chemistry. I'm definitely not a physical chemist, so we're not going to go into detail here. But I will tell you that nuclei do have this property of spin. Different types of nuclei, meaning different isotopes of atoms, will have different numbers of spin states. To be able to detect a nucleus by NMR, it has to have 2 spin states. 2 and only 2 spin states. It turns out that the proton and the C13 nucleus have 2 spin states. And those 2 spin states are called +1/2 and -1/2. So you might ask, why didn't the physicists call it +1 and -1? Well, the answer is because they're physicists. They can't do anything simple or straightforward. They've got to make it more complicated for the rest of us who aren't physicists. So we can blame a lot of the aspects of spectroscopy that don't make a lot of sense on the physicists, and this is one of those areas. Okay. So we're going to be detecting protons and carbon-13 nuclei, but not deuterium. That doesn't have 2 spin states. We're not detecting carbon-12. So these are the 2 nuclei that we're going to be detecting in NMR spectroscopy. And so the spin states are derived from the fact that when a charged particle is in motion, it creates a magnetic field. Okay, this is another principle of physics. And so when we have a nucleus spinning, there's a magnetic field associated with that motion. In the absence of an external magnetic field, then those nuclear magnets are going to be randomly oriented. They're going to be pointing off in various different directions. Okay? But when you apply a magnetic field, then the nuclear magnets are going to be in one of 2 spin states, one of 2 energy states. They're either going to be aligned with the applied magnetic field. These ones right here are aligned. This B naught, that is the term that's used, the variable that's used to indicate magnetic field strength. So the applied magnetic field is pointing up. So we have roughly half of our nuclei oriented in the same direction as the applied magnetic field, and roughly the other half oriented opposing the applied magnetic field. Okay? So we have those 2 nuclear spin states. And when we apply a magnetic field, they either line up with or against the magnetic field. So the next diagram I'm going to draw is very important for understanding the concept of NMR spectroscopy. So what we have here are the 2 nuclear spin states. And as we increase the applied magnetic field, the difference in energy between those nuclear spin states also increases. Okay, so the difference in energy between the 2 nuclear spin states is proportional to the strength of the applied magnetic field. So what we do is we choose a magnet that has the proper field strength to put the difference in energy between those spin states in the radio frequency region of the spectrum. Okay? So I'll just show you on this graph. If our magnetic field strength was right here, then our 2 nuclear spin states would be here, and this would be the difference in energy. If we had a stronger magnet, now the difference in energy between those 2 nuclear spin states would be up here. Okay? So if we have the magnetic field strength such that the difference in energy is equivalent to the energy of photons in the radio frequency region of the spectrum, if we irradiate our molecule, with radio waves of that frequency, that will cause the lower energy nuclei to undergo a process called spin flipping. Their spins will flip, meaning that they'll go to the higher energy state. Okay? After you stop the pulse of radio frequency energy, the high energy spins will relax to the lower energy spin state. As they do so, energy is given off, and that is what is detected by the NMR spectrometer. Okay? These differences in energy, even though they look pretty big here, they're actually pretty small. So at equilibrium, you have pretty close to a 50-50 population. It's maybe 52-48 or 53-47, with, of course, more of the nuclei in the lower energy than the higher energy state. But when you pulse at the right frequency of radiation, you flip them all to the higher energy state, and then a little more than half of them will relax back down to the lower energy state, giving off energy that is detected. Okay, so that's how we detect protons or nuclei in NMR spectroscopy. We irradiate them, promote them to the high energy state, and then we detect energy as they go back down. Any questions about that? Yes, go ahead. I can't. Maybe a physical chemist can, but I don't know exactly what it looks like. So, but I do know what an NMR spectrometer looks like. So here we have a schematic of an NMR spectrometer. So we have a superconducting magnet. And that magnet has to be cooled to very low temperatures in order to work, right? Superconducting magnets only operate at low temperatures. So we use both liquid nitrogen and liquid helium to do this. Liquid helium is very expensive. There's a worldwide shortage of liquid helium, due in part to the fact that the same technology that's used for NMR spectroscopy is used in MRIs. So any hospital that has an MRI machine has a superconducting magnet that it has to cool using liquid helium. Okay, so liquid helium is expensive. We just installed a helium recovery system. I don't know exactly how that works, but it allows us to recapture at least some of the helium that boils off in the process. Okay. We put our sample in a solution that we insert into a tube. As we'll talk about in a couple minutes, that solution is a deuterated solvent. Deuterated chloroform, or CdCl3, is the most common solvent that we use. Chloroform is CHCl3. We use the deuterated version because we use deuterated solvents in NMR spectroscopy. You can think about why we do that. We'll come back to it in a couple of minutes. And so then you have a console that has the electronics that controls the radio frequency pulses and also detects the energy. And then you have a workstation with a computer that sends the commands and does all the math that allows us to deconvolute the energy to get a spectrum. So the magnets, the unit of magnetic field strength is Teslas. But that's not a very convenient unit for us. So our magnets are referred to, their magnet strength is measured in megahertz. And so megahertz is frequency, that's not magnetic field strength, but what it is the strength of a magnet that will cause 300 megahertz radio frequency radiation to cause a proton to spin flip, okay? So a magnet that will cause spin flipping of protons at 300 megahertz is called a 300 megahertz magnet. A 500 megahertz magnet is stronger and will have a bigger difference in energy between those spin states. Okay? At BYU, we have 3 NMR spectrometers. We have one that's 300 megahertz and 2 that are 500 megahertz. Right? These are pretty strong magnets. You don't want to get close to them with credit cards or keys or anything like that. Okay? All right, so let's take a look at a spectrum and see what kind of characteristics we have on the spectrum. Okay? So the first thing we'll note is that there are two peaks. This is of methyl tert-butyl ether, a molecule we've talked about a few times in class. There are two types of hydrogens in this molecule, so we see two peaks in our NMR spectrum. But based on what I've told you so far, you would expect all hydrogens to show up at a single place. It would be that resonant frequency or the spin flipping frequency for the protons based on the magnetic field that's applied. But that's not the case. The reason for that is that all organic molecules have electrons, and all electrons are in motion. And as we know from physics, anytime you have a charged particle in motion, you have a local magnetic field. And so the electrons that are moving in a molecule create a local magnetic field that opposes the applied magnetic field of the spectrometer. That is referred to as shielding. So if we have a set of hydrogens that has more electrons nearby, it's going to be more shielded. It's going to feel a smaller amount of the applied magnetic field than a set of protons that has less electrons nearby. And so, based on the shielding or the lack of shielding, which we refer to as de-shielding, our different sets of hydrogens are going to feel a different percentage of the applied magnetic field. And so they will require slightly different energies to undergo the spin flipping, and therefore will show up at slightly different places in the spectrum. And we'll figure out which sets of protons will show up at which locations after Thanksgiving. That's a topic we will get into next week. But for now, we just want to understand why there's more than one peak in our spectrum. So we have intensity on the y-axis. On the x-axis, we have something that's called chemical shift or delta. Those are synonyms of each other. And delta is measured in parts per million. Okay? This is a frequency, a measure of frequency, but this is not a unit of frequency. The reason is that frequency is dependent upon the strength of the magnet we're using. We would get a different value for the same compound if we took its NMR in our 300 megahertz instrument versus if we took the NMR in the 500 megahertz instrument. We don't want that. We want a universal scale that's independent of the magnetic field strength. And that's the delta, or the chemical shift scale. Okay, and that is equal to the resonant frequency of the signal, or the set of hydrogens. That's measured in hertz. We're going to subtract from that the resonant frequency of a reference molecule, which is known as TMS, tetramethylsilane. We'll tell you what that is in a moment. And we divide that by the frequency of the spectrometer. Of course, the magnet doesn't have a frequency, but I told you how we can express the strength of the magnet in frequency units. And so the frequency of the magnet, which is measured in megahertz, is in the denominator as we calculate the chemical shift position of these signals. Okay? So TMS is tetramethylsilane. So the nice thing about this scale, as I'm drawing this molecule, is that it's independent of frequency. When you divide hertz by megahertz, you get parts per million. So you've gotten rid of the frequency. That's why we have parts per million here as our scale, because we're dividing hertz by megahertz. So silicon is less electronegative than carbon. So the electrons in these silicon carbon bonds are polarized towards the carbon. So the electrons in these sigma bonds are shielding the hydrogens in these methyl groups. So the hydrogens on carbons attached to silicon are more shielded than other hydrogens you would find in an organic molecule. So they're going to show up at the right end of the spectrum. They're going to show up at 0, and you're not going to find other hydrogens below that on our scale. So that's why tetramethylsilane is the reference molecule that is used to set this chemical shift scale. Now, why do we have bigger numbers to the left and lower numbers to the right? I don't know, but we'll blame the physicists for that. That, again, is their fault. And then there's two other terms that don't make a ton of sense: downfield and upfield. So downfield is a higher chemical shift value. Upfield is a lower chemical shift value. Again, it's counterintuitive. Once more, we blame the physicists. It has to do with the conventions that are used for referring to magnetic field strength. I don't know those conventions well enough to explain why. There is one thing that does make sense, though. We know that if a peak shows up in the upfield direction, those hydrogens are shielded by electrons in the molecule. So that means that if it shows up in the downfield direction, it's going to be de-shielded. So we can say that downfield correlates with de-shielding. Okay, so at least that makes sense. Okay, so if we see a signal that is downfield, so this, because this oxygen is electronegative, it's pulling on the electrons in the carbon-oxygen bond, this methyl group is de-shielded compared to these methyl groups, right? That's why it shows up more downfield, okay? All right, the last thing we'll say about NMR today is a question I will ask you. I said that we like to use deuterated solvents to dissolve our samples to take NMR spectra, and deuterated chloroform is the most common one. Why do we use deuterated solvents? Yes, Tyler?
Because the deuterated hydrogen does not have spin.
It has different spin states. I'm not sure how many it has, but it doesn't have the 2 spin states. So we're not detecting deuterium by NMR. So our solvent does not interfere. We're only seeing the sample, the sample molecule. Although that is not 100% true, because it is impossible to get 100% deuterated solvent. It's usually 99 point something percent. And in a real NMR spectrum, CHCl3 shows up right around 7.2. So you know that this was computer generated. This is not a real spectrum because there's no peak at 7.2 that would be for the residual CHCl3 that would be present. All right, we'll stop there. Have a happy and safe Thanksgiving, and we will see you online for the remainder of the semester and in person in January.